everyone. Today I'm going to be telling you a little bit about the work that I've been doing since being at GNS. I've been doing this project with Liz Keller, who is the project lead, and Anne-Marie, who is my team leader. This project is funded by the New Zealand Ministry for Foreign Affairs and Trade. And the general focus is looking at a probabilistic assessment of coastal inundation in the Pacific. So a little bit of background just to start off. Sea level rise is a particularly significant issue for the Pacific. Much of the region is lower socioeconomic and has a lot of its community based very close to the shoreline. In the past, we've seen that inundation events can cause significant damage and loss of life. And under sea level rise, due to climate change, as well as changing wave conditions, we expect that these will increase. However, presently, we don't really have a good way of translating the excellent science that is done by our colleagues into information that can be used by Pacific governments and community groups and researchers across the Pacific. So this is the space that this project fits into, where we're trying to, provide them with a tool that they can use to understand specific aspects of the inundation problem better. So to give you an idea of the kinds of spread in information and data that we have, I have here just a few sea level rise projections. So the colors here indicate different emission scenarios. So we have very low emission scenarios, so RCP 2.6, we also have 4.5, and then the high emissions 8.5 scenario. And then I have three different ice sheet configurations. So in each of the panels, you have COP 2014 at the top, DeConto and Pollard 2016 in the middle, and then DeConto and Pollard 2021 down the bottom. We don't need to go too much into the specifics of these particular projections, but I guess what I wanted to illustrate with this was that there is a significant range in potential sea level rise in the future. So for example, at 2100, you could have an upper bound for an estimate of sea level rise of 2.5 meters. But then conversely, you can have a possible lower bound of maybe around 30 centimeters projected sea level rise. So there's this huge variation in potential sea level rise projections, and it's even bigger when we get to wave climate. So what we need is a tool that can access these kinds of information and provide a probabilistic output that can be interpreted by non-technical people so that they can better understand what the science actually means for them on a local community scale. So that's the space that we're fitting into. To do that, we're using Bayesian network models. So the idea is to develop a framework that we can that can be flexible, that we can adjust and apply to different locations and answer specific problems. So Bayes nets are a perfect candidate for such a model because they are flexible. And importantly, they're quite a visual tool as well. And that's important for us for on a communication piece as we're trying to convey, how the different variables in the system fit together and what's important and what's not, and workshop that. We're doing this project in partnership with SPC, the Pacific Community, and the Government of Kiribati, focusing on specific regions. In the long term, we hope that this work will feed into future adaptation projects. But I want to focus on the work that I have done at Tarawa, Kiribati, which is sort of one arm to the project. So this is Tarawa here. It's an atoll, and South Tarawa is the capital. It's very low lying. The highest point in the atoll is about 4 meters above sea level, but the majority of the population sits within 1 meter above sea level. So it's very vulnerable to the effects of inundation and sea level rise. Additionally, it's low socioeconomic and with little coastal defense infrastructure. But also it actually has a very high population density. So even though it's quite small, it's actually very densely packed. So to give you a bit of an idea, there's about the same population density in the south of the island as there is in Singapore. So there's a lot of people per square kilometer. And so what we're doing what I've been doing in this particular part of the project, looking at Tarawa, is firstly starting off with understanding the water level at the shoreline. So the water level at the shoreline is sort of the first piece in understanding the inundation problem. So this diagram here outlines some of the mechanisms that are important that need to be considered in a network that can be used for estimating the total water level at the shoreline. So first of all, we have waves that are generated offshore. So particularly through storm events and cyclones, but also just everyday weather patterns, you get waves that are generated offshore. These travel to the island and they intersect the reef. Depending on the reef shape, its width, depth, the slope, its roughness, it interacts with the waves differently. And so different amounts of energy is dissipated depending on the reef characteristics. Some of the waves and their energy make it over the reef, and then they run up onto the shore. And so then you get a certain component of water level at the shoreline, which is raised because of the wave action. So that component is then added together with the tides and the mean sea level to get the total water level at the shoreline at a particular location for a given time. So all of these variables need to be incorporated together into a network to be able to estimate that total water level. So we've been working very closely with SPC, and they have very kindly provided us with data as well as model output, which has enabled us to be able to do this project. So we're very thankful to them. So they provide us with mean sea level and tidal data, which is measured data from 1993 to 2019, and it's hourly as well. As well as we have offshore meteorological data, so we have wind speed and direction. And then they have used a hydrodynamic model to calculate what the waves are offshore, and then use a nearshore model to then translate that over the reefs into what the waves are like at the shoreline. So they provided all this data to us so that we could use this as a basis for the network. I should say that there are sort of two classes of points, and I'll go into detail a little bit more about the mechanisms soon. But we kind of have points that are on the lagoon side of the island, so on the inside, which is represented here by this point. And then we also have points that are on the outside of the island. So they experience different conditions. And so we need to conceptualize two networks that address the physics of them separately. So defining the network, I use k-means as a way to cluster the data into the states that I use to define the nodes in the network. I built the network using the SMILE engine through the use of the PySMILE wrapper. So I've tried to design the system to be a flexible framework so that as we translate it to different locations and use different data sets, that we're able to tinker with the model just in the code base pretty simply so that it runs and produces standardized outputs. I tried learning the structure initially from the data and the climate model output that was provided to us by SPC. However, I couldn't really get a sensible network structure from that. So then I used our understanding of the physics of the system to define the relationships in the network. I then use expectation maximization to define the conditional probability tables. So I have a few conceptualizations of the networks, and I just want to kind of show you two kinds today. So this is the first kind. So what this is there's two networks here. So at the top, we have the ocean side, and the bottom, we have the lagoon side. So two different kinds of networks for the different locations in the island. So on the ocean side, what you have are the wave characteristics offshore. So the wave period, the wave height, and the direction. That's combining together with the reef characteristics. So the depth, the slope, and the width, as well as the direction that the shoreline is facing. Combining that with the mean sea level to get the total water level, excluding the tide. I then add in a node as well for tide to calculate what the total water level is at the shoreline. Now, the reason why I have taken out tide is because on a typical day, you have your signal for total water level is dominated by the tide. And so if you want to use the network to understand how the waves, for example, are impacting it, it's quite hard to tell without first taking out the tide. So adding in this extra step in here enables us to have a better idea of that. On the lagoon side of the island, we have wind offshore and the waves offshore. And what these do is essentially, depending on which direction the waves are going and which way the wind is going, you can have this process whereby you essentially push water into or out of the lagoon. So that, combining again with the mean sea level, gives you the total water level without the tide. And then I add in the tide then after that. So I train the network using all of the data. Well, I bootstrap the data, but from all the locations across the whole time period, 1993 to 2019, just to get a mean view of the problem to start with. So by bootstrapping the data, I evaluated the skill of the model at predicting the water level at the shoreline. So I've represented this here using a confusion matrix. So at the top where it says actual values, that's the actual value that was predicted by the hydrodynamic model the SPC provided to us for the total water level. And then down the left-hand side, you have the predicted value. Now, base nets obviously provide a probabilistic output. So what this is the most likely value that the network is suggesting for the total water level. As you can see, most of the values fall along the diagonal, which means that the model is doing a pretty good job at predicting the same values that the hydrodynamic model was. So that's pretty good. Maybe plus or minus 1 bin. So there is some error there, but it's not too bad. I'm just going to shut my window real quick because there's ambulance that keeps driving past and then you can't hear anything. So I'm going to break the rule of never doing a live demonstration in front of an audience, but I'm going to do it and let's hope it works. So I guess part of the problem really is that we want to not just develop the BayesNet, but we want it to be in a form that's accessible and use it as a bit of a communication piece. So what I've been working on is using Python to make interactive plots and maps so that you can change your evidence that you set in your network and then see how it responds in a spatially explicit way. So this is an example of a prototype I have. So up the top, there's a handful of drop downs, which are variables in the network that you can set. And then down the bottom, there is the map. So as you change them in the drop downs, it then updates in real time and will give you an indication for how you expect the total water level anomaly to change in response. So for example, I'm going to take tide as an example because that is the variable that changes the most. So for example, if tide is very low, we can see as from the colors here that the total water level anomaly goes right down. So the cool thing about this kind of a tool is that we're able to zoom in and we can zoom into the island and have a look at specific features. Perhaps we want to look at where the airport is and what we expect the water level to be just off the shore there, or there's a hospital just down here. So it's sort of, it's just the beginnings, but it's the start of using of this network to actually like understand which areas, I guess, are most vulnerable to inundation. We're also able to change it so that we can have a look at a satellite view as well. Okay, so I'm going to flip back to the presentation. And I just want to quickly fly
14
through.
minutes, Shannon.
Okay. All right. Well, just to say, we've also been doing some work at using dynamic Bayesian networks. And I won't go into the details of that, but I've started applying it to specific situations where there have been inundation events. And we won't go into too much of the specifics because we're out of time here, but just to say that what I've found is that it's possible to actually use these networks to see how the water level from waves changes in response to specific events. So this is a cyclone that occurs here, and you can kind of see this is the colors represent a probability distribution, and you're moving through time. And so you can see that the likelihood, which is it's more red if it's more likely, sort of goes from being like very low water levels, and then when a cyclone hits, it starts to increase. So the next steps are really to kind of look at this problem in a more dynamic sense. Special thanks to Anne-Marie and Liz, who are my collaborators on this project, and Hervé and Antonio for all of the data they provided to us, as well as Patricia and Nigel, who have been, or Katrina, sorry, who have been key helps in this project. Thanks, everyone.
Great, thank you very much, Shannon. Do we have questions? Bruce.
Thank you very much. Shannon, outstanding work. That's really interesting. Have you been able to address or incorporate sort of very rare intermittent extreme events?
Yeah, that's a good question. And that's kind of where we're at with looking at it in a dynamic sense. The first part that I'd shown you was more just looking at what was happening like on an average sense, but then, yeah, it does seem that we are able to model what's happening over the course of a cyclone. I've looked at a few cyclone events, and you do see that the total water level does seem to respond in a sensible way. But in terms of actually like forecasting yet with that, I haven't done that yet. But yeah, that's sort of like, that's the next step in this part of the project.
Thank you.
Do we have another question for Shannon?
Sure, I've got one. Shannon, what do you think the potential long-term management implications of this work and your tool might be?
It's a good question. I mean, I guess we'd hope that, you know, so the government of Kiribati, for example, lots like other governments in the Pacific, have to make decisions about where they put infrastructure, key pieces of infrastructure like hospitals and schools, but also coastal defense infrastructure. So I see a visualization tool like this sort of playing a role in that, where they can use it to sort of get a sense of what locations are more at risk than other locations, and potentially, yeah, sort of use that to factor into their decision making for where they put things. And then also considering it under different sea level rise scenarios. So I didn't really touch on that, but because the mean sea level is affected by the melting of Antarctic ice, essentially, as well as just, well, increasing sea levels, you know, depending on what emission scenario we go down, you see different levels of inundation coming from that. And so I see sort of a way in which you can kind of use this tool and say, okay, if we're kind of heading down this emissions pathway, what do we expect to see? What emissions pathways should we plan for? What should we discount? That kind of thing.